All right, today's big day. Big day, we talk about the unit circle. Now, of course, we've already started the unit circle and put degrees and radians on it, but today you get to see why we really kind of use it more so than just degrees and radians, and we're going to build the unit circle today. So thanks for being here with me. Now, we're going to start with what you do know or hopefully remember from the little bit of trig that you have had, which is just SOHCAHTOA. And so just to clarify what SOHCAHTOA really is representing, because you probably just remember the acronym and then just run with it. But since we're in a trig class, this should sort of really make sense what we're doing. So let's say you have some particular angle. They've put it right here. Here's theta down here. And then you have these three sides in reference to this angle. This is the side across or the side opposite of it. This is the side that's next to it. And I say the side, the leg is, and we call that adjacent. But then you always are going to have a hypotenuse because these are all right triangles. So you have your hypotenuse and the other two legs are either the opposite or adjacent. Now, if you were to look at the ratio of the opposite side to the hypotenuse, let me just make up some fake numbers. Let's say that the opposite side is 4, and we'll make the hypotenuse be, let's just say 8, just to keep life simple. Now, if I'm going to find the sine of that angle theta, it's opposite over hypotenuse. So it would be 4 over 8. Of that, of course, would reduce to 1/2. Now, so that means that the sine of that angle, whatever theta is, the sine of it is 1/2. Now, what I can do with this triangle is I could reduce it, but as long as I keep it the same shape, but just make it smaller, let's say it's just like this triangle right here, that's the same shape, but just smaller. If it's the same shape, then theta is still the same angle measurement. Whatever it was, it's just been shrunk. The sides have shrunk down, but the angles all stay the same because they have to add up to 180. Now, what that means, though, is if I shrink it proportionally like that, then the ratio of the sides would stay the same. So if this was like a 2 now instead of a 4, well, then this would have to be a 4 because the sine ratio would still be opposite over hypotenuse. Now it's a 2 over 4, which again reduces to 1/2. And so it's that ratio would stay the same. If I made a triangle that was really big, maybe now this side is 6. Well, this side would be 12 because that ratio will stay the same. It'll still be a 1/2. All right, so that's what the sine, the word sine, actually is representing, is it's always going to be the ratio of the opposite side to the hypotenuse given a particular angle measurement. Now, as that angle changes, then that ratio would change. All right, so this is the SOHCAHTOA. These are your ratios. I'm going to hope you remember that. We're going to move on. Now what I'm going to do is I'm going to take some triangles and I'm going to put them into our unit circle. And they're not new triangles. They're the same ones that we would have been using all along. It's just that I actually draw the full triangle in here. So you can see like this orange triangle. This is, and to be honest, if I were you, I'd take a minute, pause the video and go get some colored pencils, some markers, something to designate colors because this gets pretty cluttery without it. Gets pretty cluttery with it, but all right. So moving on, the orange triangle, we know that this right here would be a 30-degree angle because that first mark on our unit circle is a 30. I know that in the green triangle here, this would be a 45, and in the purple triangle, this would be a 60. So I've drawn these over here, and they actually end up being, when you think of what those angle measurements would have to be, the way that I've dropped it straight down every time creates a right angle in all of them. And then the other ones are forcing this into our special right triangles, which is why we spent a little bit of time going over the special right triangles. So what I need us to do then is, in this situation on our unit circle, I haven't really talked a lot about it, but the reason it's called a unit circle is because the radius is assumed to be 1 unit. So when you think the radius, this is your radius, it's 1 unit, but this is also a radius, which we've put right here and we've said it's 1. Or this is a radius and we've done it here and said it's 1. And so this hypotenuse in all three of these triangles is always 1. So let's go back and see if we remember how to do this. If your hypotenuse is 1, then your short leg would be 1/2. And if your short leg is 1/2, then this is 1/2 root 3. We would probably just write it as a root 3 over 2, like that. And actually, the orange triangle and the purple triangle, they're the same triangle. They're both 30, 60, 90s. They both have a hypotenuse of 1. It's just they're kind of turned differently. But in this case, the short leg is down here, so it's a 1/2. And then the long leg is on the side here. It's a root 3 over 2 now. Same triangle, just oriented differently. Now, the green one is a 45, 45, 90. That's different. If the hypotenuse is 1 on that one, remember that you have to divide by root 2 to get to your legs. And then you rationalize and you have root 2 over 2. So both legs here are root 2 over 2. Now, this is important. I'll show you why in a minute. I'm going to have to go on to the next slide, but you're going to look back at these triangles and these measurements that we have on there. Again, tying some concepts together here. On this slide, what I would like to do is I would like to find the cosine of all of these angles that I have on my unit circle, anywhere from the 30, the 45, the 60, even up to the 90. So if you think of cosine, remember that it's adjacent over hypotenuse. So in the orange triangle, let's start with that. I'm kind of limited on my colors. I wish I had an orange marker on this, but I don't. I have a yellow. Let's go with the yellow. All right. So looking at this angle right here, thought it was yellow. There we go. This angle is a 30-degree angle. If I want to find the cosine, I'm going to take the adjacent side, which is right here, and put it over the hypotenuse, which is right here. Now you have to look back. I hope you wrote down those other triangles. If not, you better pause and backtrack and go write those down. So I know that the hypotenuse is always 1 because that's your radius. What was the long leg in that 30, 60, 90? Well, hopefully you're saying, oh, that was a root 3 over 2. So I'm going to write adjacent root 3 over 2 over hypotenuse, which is just over 1. So ultimately, it's just a root 3 over 2. So now that's the cosine of a 30-degree angle. Now you could type it in your calculator. We're not doing that right now. We're just finding exact values. And there it is, root 3 over 2. Okay, next, let's try it again. I'm going to erase some things so that it doesn't get too cluttery on us. I'm going to look at the green triangle now. Okay, so for the green triangle, again, doing cosine. So I'm again interested in the adjacent side to this. And the adjacent side would be this. And I'm looking at this triangle here I should comment on. All right, adjacent is right here. Hypotenuse is right here. Well, hypotenuse again is just 1. What was the adjacent? What was this leg in our 45, 45, 90 on the previous slide? And of course, you're saying, oh, well, that was root 2 over 2. So adjacent is root 2 over 2 over 1 really just equals root 2 over 2. Okay, so at this point, I'd like to say, well, isn't the hypotenuse on all three of these triangles always 1? So do I really even need to mess with the over 1? So when I look at my next one, which is the purple, and the triangle that gets created is this one right here. Adjacent this time is short leg, hypotenuse still 1. All right, so ultimately it's just going to be the adjacent, which in the short leg is a 1/2. Okay, now that's kind of important what we just said there. Ultimately, what I'm saying is I don't care about the hypotenuse. So instead of the cosine being adjacent over hypotenuse, the cosine always just ends up being the adjacent, because the hypotenuse is always 1. Now you might say, well, yeah, but this is a special situation. It's just this, it happens to have a hypotenuse of 1. But remember what I said earlier, I could take this unit circle and I could make it bigger so that it has a hypotenuse of 2 or of 7. But as I make that circle bigger, not only is the hypotenuse getting longer, but the adjacent side is, and it would be getting longer proportionally. So it would still reduce down to this same value or this same value or this same value. So the 1 is just making my life easy today. That's why we do that. Okay, so now I have a tricky one for you. So now I want to find the cosine of 90. The cosine of 90, that's tricky because I can't draw that triangle. I'm going to erase a little bit here. If I try to draw a triangle at a 90, it's pretty much just going to go straight up and straight back down. That's not even a triangle. So this is why it's very important that we have caught on that the cosine ultimately is just the adjacent side. Now, let me go a little bit deeper to that. When I say the adjacent side, did you notice that the adjacent side was always this bottom leg? This was the adjacent, and then in the green triangle, this was adjacent. In the purple, this was adjacent. So ultimately, what it's telling me when I say the adjacent, it's just how far over it's going. That's your adjacent leg. So in this case, I'm over root 3 over 2. In the green one, I'm over root 2 over 2. Purple, I'm over 1/2. How far over am I on the red? I'm not over anything. So that means that the cosine at 90 would have to be equal to 0. All right, so again, this is important because the cosine is the adjacent, but I'm not even so much worried about that, is now I'm saying that the cosine is how far over I'm going. It's my horizontal distance. And if you think about it, the horizontal distance, if you're actually thinking like this is the origin right here, and then this is an ordered pair over 1 up 0, and this is an ordered pair over 0 up 1, like on a coordinate plane, ultimately, this leg that we're talking about right here, how far over, it's an x coordinate. All right, so I'm going to jot that down. I know it's feeling kind of confusing for a minute here. Hopefully it'll start to make sense. So it's the horizontal distance or it's the x coordinate. Another way to think of it. All right, I'm going to bail. Here we go. Let's move on. Oh, look, it's the same picture, except now I'm going to be looking for the sine of all of these angles. Okay, when I look for the sine of an angle, it's opposite over hypotenuse. And what happened last time with all the hypotenuse? It's always 1. So ultimately, the sine is just going to be whatever the opposite is. So let's look at the orange to start with. So when I'm looking at the orange triangle here, here's my theta, here's my angle, and sine is opposite, which would be this, over hypotenuse. So you have to look back at the slide that tells you the side measurements on a 30, 60, 90. This is your short leg. And the short leg is a 1/2 over 1, just going to be 1/2. Let's try it with the green triangle. On the green triangle, when I do the sine of this 45-degree angle right here, opposite is this, hypotenuse is 1. So ultimately, I just need opposite, and in a 45, 45, 90, recall that both legs are root 2 over 2. Okay, are you catching on what's different here? Now I'm going to do the purple. Here's our triangle. if I do the sine of what is now a 60-degree angle, the sine of a 60-degree angle is opposite, which is long leg, over hypotenuse, which is still 1. So opposite leg is all I really need. Opposite leg is a long leg in this triangle, and that's a √3/2. All right, so did you notice that since you're doing the opposite, now it always is representing how far up you're going. So it is your vertical movement instead of your horizontal movement, and that would no longer be the x coordinate. The sine value is the y coordinate, if you want to think of it like that. Or you can think of it as the vertical distance that you're going. Sorry, my handwriting's so bad on this thing. Okay, so now, moment of truth. Uh-oh. What happened to all my answers there? Did I goof? Okay, hopefully you had those written down. All right, so sine of 90. Here's my 90. So looking at that, if the sine is really going to be your vertical distance, how far are we going vertically there, do you think? Hopefully you're saying, I'm going 1, going up 1 right there. The sine of 90 is 1. Okay, let's look at what we're going to do with that info. Now, if this is just a little bit blurry still, I really think it would be worth your time to just back up and watch the cosine and the sine slide all over. Just watch it one more time until that kind of sinks in just a little bit stronger. All right, this is actually 2 slides in your notes, but it kind of is just a cleanup version of here are the different triangles that you should see in your unit circle. You've got the 30, 60, 90 when it's kind of like laying on its side and the short leg is over here. Or you have the 60-degree where that opposite side is now the long leg. Same measurements, just flipped. Then we have the 45, 45, 90s, and your over and up are always the same. They're that √2/2. All right, you have this in 2 slides because it got a little bit tight and messy on 1 slide. What you have to recognize now is that these 3 triangles that we just did, everything was in the first quadrant. But those same 3 triangles will happen in all the quadrants. It's just going to be a reflection. It's just going to flip over the axis, and then it's going to be over there. But the measurements will all stay the same. What is going to change is the sign, because we do look at this like these are 4 quadrants. So anything that we've been working on has been in the first quadrant, so everything is positive. But over here, our x value will be negative while our y values are positive. In the third quadrant, you're going left and down, so both are negative. Fourth quadrant, you're going right, so your x's will be positive, but you're going down, so your y's will be negative. All right, I'm going to do this. We're going to fill this in. So this is 2 more things we're adding at each dot. If you need a new color for your unit circle, pause the video, go get a new color. We're going to add this in. You don't need to put this in your notes. You need to put this in on your unit circle. All right, so here's the deal. I wrote this up here to kind of go over. Remember that the cosine value is your horizontal movement, so it's like your x. The sine is your y, so is your vertical, so it's your y. And so a quick way to write this on each dot is to write it as an ordered pair, just remembering that cosine is x and sine is y. A little trick to help remember that, I guess, that I just always did is I remembered that cosine and sine, it's alphabetical. Cosine comes before sine. So x comes before y. That just helped me remember for sure which way it went. Okay, I'm going to do this in groups. And I'm really actually going to start with the ones that aren't even triangles. So that's what we call the quadrantal angles, the ones that fall on the axes. So if you think of this one over here, all we're doing is we're going to write the ordered pair of this dot right here. So the ordered pair of that is over 1, up 0. What that really means to us, though, we write it like that But what that means is the cosine of 0 degrees or 0 radians, or for that matter, 360 and 2 pi, because they are coterminal and they land in the same spot. The cosine of 0 is 1. The sine of 0 is 0. Okay? Quadrantal angles are all going to come out real nice like this. So for this dot, I'm over 0 up 1, meaning that the cosine is 0 and the sine is 1 of a 90-degree angle. Now I'm over here. Now here we go with some negatives. I'm left 1 up 0, which means my cosine at 180 degrees is actually negative 1. Okay, down here, over 0, down 1. Right in the ordered pair, but ultimately what I'm writing is the cosine and sine of each one of those angles. Okay, so the next one I'm going to go to is I'm going to look at the 45s. And the 45, now I'm going to draw all over this, but I really don't want you to, because it will get to be a mess and then you won't be able to read your circle. But what I want to look at here are the 45, 45, 90 triangles. You can see that this is the one that we did in class. And we're always dropping straight down to the x-axis. Every time you draw that triangle, it goes straight down to the x-axis. And that's where that right angle happens. But that triangle also happens right here. It's the same triangle. It happens down here. Same triangle. It's just oriented differently. But they're all the same triangle, so the numbers on them are all the same. The hypotenuse is always going to be 1 because that's the radius, and the two legs are the same. This leg and this leg, if you'll peek back at that triangle, those are both root 2 over 2. Root 2 over 2. Okay, you didn't do that, right? Didn't write any of that, because now I'm going to wipe it and get rid of it because it's going to get too cluttery. So if I get rid of all of that, I'm just going to go around and write, because it's a 45, 45, 90, the sine and the cosine are always going to be the same. They're going to both be root 2 over 2, root 2 over 2, every time. Except, depending on the quadrant, sometimes they'll be negative. So over here in the second quadrant, the cosine is going to be a negative root 2 over 2, because you're going left. Sine is going to be a positive root 2 over 2. All right, third quadrant, both negative. And fourth quadrant, I'm going right, so the cosine will be positive, but I'm going down, so the sine is negative. Now, if you're feeling ambitious, and we haven't done anything with the calculator, but you could try some of these in your calculator if you wanted. Like you could do the sine of 0, and hopefully it would shoot back a 0. You could do the sine or the cosine of 0, and it would give you a 1. If you did the cosine of 45, it's going to get you the decimal version of this. Now, it is worth noting before you go do that you do have in your calculator a mode, and it matters on if you are in degree mode or radian mode. So when I say the cosine of 45, you'd want to go check the mode and make sure that it is in degree mode before you did that. If you said, what's the cosine of pi over 4? Well, then you'd want it to be in radian mode. And then both situations, you would get the root 2 over 2 as a decimal. Okay, now I'm going to work on 30, 60, 90. So what I'm going to do is I'm going to draw this 30-degree one right here. You got this triangle. Can you envision where else that triangle is, but just a reflection? All right, I could flip it over and it would be right here. Or I could flip it over the x-axis and it would be right here. These are all what I call like the long, skinny 30, 60, 90s. And then you'd have another one over here, long and skinny. Because in all four of these triangles, your cosine, how far you're going horizontally, is always the long leg. Whether you're going left or right, this is the long leg. And the sine value, the y, is always the short leg. So in all four of these triangles, the cosine is the long leg, root 3 over 2. need a new color here. Let me go back to blue. Cosine is root 3 over 2 because it's how far you're going horizontally. Your y value is the short leg, so your sine is that 1/2. Every one of these 4 triangles is going to have the same thing. The only thing that will change is what's negative. So these two have a positive x value, so root 3 over 2. But on this one that I'm writing now, I'm going down, so it'll be a negative 1/2 for the y value or for the sine. Okay, on this side, on the left, I've got a negative root 3 over 2 for my cosine, negative root 3 over 2 for my cosine here. But the y values that are 1/2, this one is up 1/2, so it's positive. This one's down 1/2, so it's negative. All right, almost done. So close, so close. Got to erase. I got one more set. It's the tall, skinny, what I call the tall, skinny 30, 60, 90s. So that's this one here. You go up the line there, straight. Whoa, got a little crazy. Undo that. Draw to the 60, then straight down. That's where your right angle happens. And you have that. And then you're trying to find all the triangles that would look like that. Well, so the tall, skinny ones, that would be one. This one here would be one. It's just a reflection over the y-axis. Or if you took those and reflected over the x-axis, it'd be these down here. Now, what happens on all of these triangles is that how far you're going horizontally is now your short leg. So that's your cosine. And if it's your short leg, your cosine now is always going to be a 1/2 because that's the short leg in that triangle. Again, this is always going back to that one slide where we had all 3 triangles and we found the missing sides. All right. So cosines are all 1/2 and the sines are all your long leg. So your sines are always root 3 over 2s. So here we go. 1/2 is how far over. I'm up the long leg, root 3 over 2. On the one in the second quadrant, I'm left a half up root 3 over 2. Down in the third quadrant, I'm left a half and I'm down root 3 over 2. And this last one, very last one, I'm right a half down root 3 over 2. Now these numbers that I have written all over the place, I know it feels like, oh my gosh, I'm supposed to remember all this? Yeah, you are. There's really only like 3 key numbers. You've got to know the root 2 over 2 goes with the 45s. And it is the x and the y are the same on all of those, root 2 over 2. And then you just have to remember the 1/2 and the root 3 over 2. Those 2 numbers go with your 30s or your 60s. You also need to know that 1/2 is your short leg, where root 3 over 2 is your long leg. And you can type that in your calculator. I know the short leg is 0.5. Well, heck, I'm going to do it right now. Let's see. If I did a square root of 3 and I divided it by 2, I get 0.866. So the long leg here, that's a 0.866 versus the short leg, which is a 0.5. So that's another way you can check, I guess, to make sure that which one's which. Okay. Now with that, we would stop in class and we would just practice this. You have a worksheet. I have flashcards in Google Classroom, and I know that you've been practicing your degree in radian that way. Now you're going to move to the next level. You're looking at the sine and cosine flashcards. Don't do tangent yet. We're not doing that yet today. So maybe take a break yourself right now. Go practice a little bit. See if you can figure some of these out. The idea is that if I ask you what's the cosine of a particular, like what's the cosine of 120 degrees? So here's what you're doing. In your head, you're saying, all right, I know that 120 is right here. And cosine is the x. So I have to envision this triangle. I'm not going to draw this triangle every time, but I can envision that triangle and say, oh, that would be my short leg. I'm over the short leg. The short leg's 1/2. So the cosine of 120 is 1/2. However, I went left, so it's -1/2. Now, the idea is you're not looking at this. You have this kind of as a basis, but you're not going to be looking at this constantly. We don't need a cheat sheet. We got this. Okay, let's try another one. Let's say, so I'm going to practice with you on a few of these, and then the idea is you go practice on your own. So let's say we have an angle. Let's do 7 pi over 6. So the first thing is you got to know where 7 pi over 6 is. I know that you know that 7 pi over 6 is right here. So what you're envisioning then is, okay, at that spot, I would be over the long leg, down the short leg. So cosine is the long leg, sine is the short leg. I don't even think I asked what I wanted yet. So let's say you wanted the cosine of a 7 pi over 6. So the cosine is the x, that's the long leg. Long leg is √3/2. It's only 3 numbers. Well, I say 3 numbers. We do have the ones and zeros, but ideally you don't have to think too hard on those. Okay, let's try another one. Let's say we have the sine of 7 pi over 4. So first thing you got to do is get your head in the right spot on the unit circle. 7 pi over 4. 7 pi over 4 is it's a fourth, so it's a 45. It's the last one. It's right here. Now I ask for the sine value. Now I know on the 45s that everything is √2/2. But since it's the sine value and sine is the y, I'm going down. So the sine is a -√2/2. Okay, one last one. How about the cosine of 3 pi over 2? So 3 pi over 2 is actually just straight down. And if I want the cosine, I want to know the x, or the horizontal movement. And since I didn't go left or right at all, the cosine is 0. All right. It's not really a race. It's really just, can you think through it's kind of 3 steps. Get yourself in the right spot on the unit circle. Then recognize which triangle you're dealing with. Is it short leg, long leg? What is that? And then decide if it's positive or negative. Kind of 3 steps. Really need to practice. Oh, look, I even left this in my video because you should go practice. I have a bunch of practice worksheets. Maybe you already have it, or maybe you can find one in Google Classroom. I do have one last thing. Now that I know that you went and practiced, so now I have one more thing. Functions that repeat are called periodic functions. And there is definitely repetition going on in the unit circle. But it doesn't really officially repeat until you've gone one full revolution. Once you've gone one full revolution of the circle, then it will start repeating exactly the same pattern. And then another revolution, it will exact same pattern. So we call that interval that it takes before it starts repeating, we call that the period. And the period, the interval that it takes for sine and cosine to repeat, is one full revolution. So we say 2 pi. That is the period. Every 2 pi, every revolution, sine or cosine, will start repeating. What that's going to allow us to do is to find the sine and cosine of angles that aren't on the unit circle, at least not on one revolution of the unit circle. So if you look at some of these, it's kind of like when we did coterminal angles. You still just have to figure out where does it land on the unit circle. And then that sine and cosine value will stay the same. So let's look at this first one, the sine of 18 pi. And that's actually kind of nice because it's not even a fraction. So I'm going to sketch this. Now our goal is to be able to do this sort of and just envision it happening, but it's hard for me to envision in a video for you. So I am going to go ahead and sketch this. So we know that this is 2 pi. That means this would be 4 pi. 6 pi. And so all the even pi's are on this side. If I wanted 1 pi or 3 pi, it would always be over here. Odds are here, evens here. So since 18 pi is even, it would land right here where 2 pi is. And if I want to know the sign value, that's the y. So the sign, the y, is 0. All right, maybe I'll put this here for us to help you remember that it's cosine, comma, sine. This is your x, this is your y. All right, let's try again. 17 pi over 6. That's a lot of 6. I know that, I could start counting this out to 17, but I don't really want to do that, so I'm going to shortcut it. I know that this would be 6, 6, because that's 1 pi, which means this is 12, 6. And another 6, 6, this is 18, 6. Oops, went too far. I only want 17, 6, so it's the one right before that. It's right here. Okay, I want the cosine of it. I don't even have to associate it with what that is. It is 5 pi over 6, but really what I care about is where did it land? Oh, it landed right here. I want the cosine. Can you envision the triangle that's drawn there? Would your cosine, which is your x, would that be your long leg or your short leg? Are you more over or are you more up? Well, you're more over. So your cosine in that example is your long leg. And your cosine, or your long leg, is a root 3 over 2. Now, notice that we did go left, so it's actually negative root 3 over 2. Okay, so one more shortcut that I'm going to write here for you. You got the root 2 over 2, that's on your 45s, or you have the 1/2 and the root 3 over 2. All right, let's keep going. We got 4 more. Stick with me. I know it's getting long. It's a very, 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 very important day. All right, next one, 9 pi over 4. Okay, fourths are on all your 45s, and I can count it out, but I'm not going to because I know this is 4/4. This would be 8/4. So 9/4 is one more. It's the one that lands right here. Okay, we're in luck. It's first quadrant, so everything's positive. And on the 45s, everything is root 2 over 2. Next one, 11 pi over 2. All right, those are halves. So this is 1/2, 2 halves, 3 halves, 4 halves. Okay, I'm going to jump bigger. This is 4 halves. 5, 6, 7, 8, 9, 10, 11 halves. All right. Now, there are other ways to do that. I'm just kind of showing you. All right, 11 halves would land there. I'm looking for the sign value. The sign is my y. So how far down did I go? I went down 1 full unit. So that's a -1. Okay, you can always also do this with negative angles. Remember, negative angles just wrap backwards. So in 11 pi over 4, well, I'm just going to go backwards here. This is 1, 2, 3, 4 fourths, 5, 6, 7, 8 fourths, 9, 10, 11 fourths. All right, I backed up 11 fourths right there. All right, the cosine. And again, we're lucky on a 45 because everything is root 2 over 2, but I am left. So it's a negative root 2 over 2. Okay, last one. Here we go. It's thirds. Oh, that's tricky because, and it sort of depends. You might be familiar with the thirds. You might like to change it into 6. So if you want to think of it as 14, 6, you could do that. So I'll go ahead and do that, I guess, since I wrote it. So I am backing up 14, 6. So again, big jumps. I can count 6, but really that's 6, 6. 12, 6. 13, 6. 14, 6. So I'm right here. This one down here at 300 or at 5 pi over 3. It's the same thing. Okay, so at 5 pi over 3, I'm looking for the cosine. That's my short leg because I'm over a little bit. and I am going right a little bit. So the cosine is 1/2. All right, I'm a big visual person. I like this to make sense on that circle and what that looks like. Another option that you could do, because I did say right here, it's really just coterminal angles. So instead of counting it out and envisioning it like that, you can do what we did with coterminal angles. Start reducing this. Reduce it, reduce it, reduce it, until it's something we know on our unit circle. So you could subtract 2 pi over and over and over until you get something. Now, in this case, you really wouldn't have to subtract very much because 2 pi would really be 12/6. So you would just subtract 12/6. That gets you to 5/6. That was right there. If you'll recall, yep, that's where we landed. So I don't know. I'm showing you visually what's going on, but you can always do that coterminal angle thing if you'd like to do that instead. Okay, I'm done. I'll stop talking. All right. Thanks for watching this. This really is important stuff for moving forward. Have a great day.